Okay, our next speaker is Dr. Gavin Collins. He received a joint bachelor's and master's degree in statistics from Brigham Young University in 2018, and then completed a PhD in statistics at Ohio State University in 2023. He recently started as a full-time R&D statistician at Sandia National Laboratories in Albuquerque, New Mexico. And his research interests include Bayesian statistics, nonparametric regression, functional data analysis, and emulation and calibration of computational models. Please help me welcome Dr. Collins to the podium.
Hey, so today I'll be presenting on Bayesian Projection Pursuit Regression, which is a method that my colleagues and I at Los Alamos, Devin Frankham and Kellen Rumsey helped me to develop when I was an intern there a couple of years ago. So let's see. Oh, now it's okay. There we go. Okay, so just a brief outline. I'll first just go over the regression framework that I'll be working in today, and then I'll talk about some different Bayesian nonlinear regression models, just to kind of give context for this Bayesian projection pursuit regression model, and then I'll go over that. So in regression, in the setting we're looking at, standard regression setting where we have inputs at X and responses Y. And our inputs will be multivariate and our responses will assume are univariate for this talk. In the regression model, we'll assume that given the inputs, the responses will be normally distributed with mean f of X and variance sigma squared. So the goal will be to learn the mean function f and the residual variance sigma squared from data. So just as an example, we worked with this hurricane data that comes from a modeling and simulation framework. And so here we have 6 different inputs: the initial sea level, hurricane heading, velocity of the eye of the hurricane, the max wind speed, the minimum pressure, and then the landfall location. And then all of this is just plugged into the simulation model. And the response that we were looking at was the maximum water level at a particular location. So of course, you could look at this response across various locations, and you'd have like maybe a spatial model or even a spatiotemporal model, but we were just looking at this univariate response. And then for the rest of the talk, I'll kind of use this simulated example as kind of my toy example. So here I'm just looking at P equals 2 inputs, and the mean function I'll be looking at is called the lim function. It comes from this paper by Lim et al. And so the mean function that we're looking at is shown on the top right here. So we have 2 inputs, x1 and x2, and then the mean function is shown in color. So one of the main goals is to estimate this function given a noisy realization of the surface. So that's shown on the bottom right here, where we have our observed response that is centered at the mean function but has a residual variance. Okay, so this slide just briefly lays out the Bayesian nonlinear regression framework in the way that I view it. So here we model the mean function as a sum of m basis functions. Those basis functions are g, and they're parameterized by theta j, right? So we have m parameters, theta, and these could be vectors. They could even be unstructured data or different types of structured data. So I'll show some examples to come, but in this framework, sometimes the number of basis functions can be learned from the data, or sometimes you just fix it ahead of time. And then the parameters, theta, will be learned from the data. And then the Bayesian framework will be sampling from the posterior distribution of these parameters. And the nice thing that comes out of this is uncertainty intervals for our mean function. All right, so here's one example of Bayesian nonlinear regression. And it's maybe the most commonly known example that kind of fits into this framework. So this is the Bayesian additive regression trees, or BART model. So each parameter here is a decision tree. So how this works: for a single tree, you plug your input parameter into the tree, and you just kind of follow these rules until you reach a bottom node of the tree. And then the prediction is given by this mu parameter at the bottom. So, if your second input is less than 0.8 and your first is less than 0.25, then your value of the basis function would be 40 in this case. And then you add up many of these basis functions to get your full mean function. And then the way that we estimate this model is using an MCMC algorithm. There's a citation here for the initial paper back in 2010 that introduces this model. So to kind of give you a feel for what this looks like, in a single dimension, your basis function would look like this on the left. It's just a step function. In 2 dimensions, you'd have a 2-dimensional step function like this one in the middle. And if you add together, I think here I'm using 200 trees. So if you add together predictions from all of those trees, then you get a representation of the mean function like the one on the right. And then the cool thing that comes out of this is the uncertainty quantification. So the top left here, I'm showing the actual mean function. The top right is the BART prediction, which is just the posterior mean estimate. The bottom left is a lower bound of credible interval of a 95% credible interval, and the bottom right is the upper bound. And so since this is a 95% interval, you would hope that the coverage of that interval would be about 95%. And if we evaluate that, it turns out to be over 98% in this particular case. And so we're actually overcovering a little bit, meaning that the intervals are a little bit wider than they should be. But this can be calibrated by changing the parameters of the prior distribution. And then I'm also giving R squared as a measure of accuracy of how well the posterior mean predicts the actual mean function. So 97% R squared here. So I won't have time to go through this in great detail, but here's another example of Bayesian nonlinear regression. It's called the BAS model, or Bayesian Adaptive Spline Surfaces. This is also known as Bayesian Mars, or BMARS. It fits into the same framework, but instead of trees, you have these tensors, and then you take a tensor product of a set of tensors to represent the mean function, and then you add together these basis functions to get your final prediction. So if you have one of these in a single dimension, it just looks like a hockey stick. And in 2 dimensions, it's kind of a 2-dimensional hockey stick, if you will. And if you add together a bunch of these, then you get something like what's shown on the right. And we can do the same sorts of evaluations. So it turns out here, we're actually undercovering in this case with 86% coverage, but the accuracy is a little better than for BART. But these, of course, vary pretty widely depending on the data set that you're looking at. All right, and so finally, I get to the main topic here, which is Bayesian Projection Pursuit Regression. So here, we have 2 parameters we're trying to learn for each basis function. We have a projection direction phi and a basis function b. So just real quickly, how this works is that you first project your features x in the direction phi, and then you'd take some nonlinear function of that projection as your basis function. So an example is shown here on the right. So the horizontal axis here is actually the projection of the two-dimensional feature. And then we have this curvy hockey stick as a nonlinear function of that projection. And I want to show you how it looks in 2 dimensions. It might make a little more sense how this is working. But then we estimate all of these parameters via an MCMC algorithm. So projection pursuit regression, you may have heard of. It was developed back in early 80s by Jerome Friedman and Ernest Dutzel. And this is the first Bayesian version of projection pursuit regression that I have come across. So I won't go into too much detail about this. This is just kind of how we form these basis functions. It involves using a ReLU to kind of zero out part of that projection space. And the rest is a natural spline. So there are a few parameters that we have to learn there for the basis function. Another thing that we found to be important is using sparse projections, meaning that this projection vector here, some of the elements can be zeroed out. And we found that this just introduces some parsimony and actually helps a lot in the prediction. But here's what it might look like. So you have your curvy hockey stick over here in 1 dimension, but in 2 dimensions, you get something that looks like this. So you can very clearly see what direction we're projecting in. And then we have like a nonlinear transformation along that projection. And then if you sum together a bunch of these, you get a good approximation of the mean function. So here, it turns out for this example, the first example I tried, Bayesian projection pursuit regression, was the worst, and I didn't want to show that example here. So I picked this one, and lo and behold, on the second try, it was the best. But I'll show a few more data sets to see kind of how well it does in general. But here the accuracy is better than the other two, and the coverage is closer to nominal at 97%. And then, so one nice thing about this model is that it is relatively interpretable as far as like a machine learning type model goes. So here at the top, this is the function we were trying to estimate in this case. So this is called the Friedman function. And you can see that it has a linear part here, and it also has like a quadratic part and then a sinusoidal combination of the first 2 inputs. And you can kind of see this play out if you look at the individual basis functions. So like this first basis function, we were only using one of the inputs in the projection. And so all of the others were zeroed out via our algorithm. And the basis function looks pretty quadratic here. And you can see that that is good because that's what it's supposed to look like in the Friedman function we're trying to estimate. So you see that quadratic part play out there. And then we have another linear part where it's supposed to be linear. And then these other 3 basis functions involve x1 and x2 and also x5. And so you're getting this linear part with x5, and then you're getting like this interaction between x1 and x2. Whenever you include multiple features in a projection, then you end up getting an interaction effect. So it's nice to see that play out. Okay, and then I'll show so this is 6 different data sets. In our paper, we looked at over 20 real data sets and over 20 simulated data sets. So it's a pretty expansive comparison. But here I'm just showing 6 that are kind of representative of what we saw in the larger study. So BPPR is Bayesian Projection Pursuit Regression. BAS is another acronym for BMARS. And then the BART model. So we're looking at these bottom 3 that I've showed today. So Bayes PPR was best on on two of these data sets actually. So the top left and the bottom lowest RMSE. BART was better in, I think, 4 of them or 3 of them. So yeah, 1, 2, 3. And so if you look at this across data sets, there's all of these are best at least once if you look at enough data sets, right? So depending on what data set you're looking at, you might want to try several of these or at least a couple to see what works best in your specific scenario. Some future work that we want to do is to figure out if you can determine kind of a priori which one of these is going to do best. So that's still kind of an open question. If you look at uncertainty quantification across different data sets, here we're trying to reach the 95% coverage, and the 3 methods I talked about today do pretty well. I think this is showing a box plot across 20 different data sets. All 3 of them do pretty well. Maybe BART is closest to best on average. Okay, and so I'll kind of wrap up quickly here. So I just showed 3 examples of Bayesian nonlinear regression. And there are some advantages of these. So they're pretty fast, especially for Bayesian models. And so like the toy example I showed with 350 data points, it's a fairly small data set, but it took like 2 seconds to fit that. And it scales pretty well with the number of data points. So if you're familiar with like Gaussian processes, they don't scale as well with the number of data points. These scale better because you're using this basis function representation. And they typically work well out of the box. So in that comparison we do in our paper, where we're looking at a whole bunch of different data sets, we just use default prior settings on all of those data sets, and they still do pretty well. But you can tweak those prior hyperparameters to try to get better performance. So I think I'll go ahead and stop there. Here's some contact info and info for the paper. You can also find the full documentation of the code on GitHub. So, thanks.
Oh, go ahead. You said your method does automatic variable selection?
Yeah.
Is that working similar to what Lasso does or different?
I mean, the effect is similar, but it's done in a different way. So how it works is when you propose, like say adding a new basis function, you'll propose like putting in these 2 features or these 3 features, and that can be accepted or rejected by the MCMC algorithm. And so it just kind of fluctuates across iterations in the algorithm, and you kind of converge on what should fit in your model. That makes sense. Yeah. Yeah.
You're comparing models of the same complexity, presumably, like number of free parameters, or what's the metric?
Not necessarily the same complexity. So for these models I've been talking about, often the complexity is actually a parameter in of itself that's learned. So you learn how many basis functions should be in the model.
Oh, I see. So it's not, there's no risk of like you could just improve add parameters forever and just do better with one model than another. You would do worse by.
Yeah, like if you go to predict on an out of sample data set, you could of course do worse by having too many parameters in the model. So the Bayesian methodology kind of has a built-in regularization into it. So when we learn how many basis functions are in the model, we actually put like a Poisson distribution on the number of basis functions. And so, if you want to limit how many basis functions are in your model, try to avoid too much complexity, you can do that by adjusting that Poisson prior distribution. Thanks.